Hello. The reason behind the preference of mine to record this short video is to show you or to present you the calculation of the total lifetime of the whole universe. But by doing so, we are in that very requisition to having an assumption which is about the presence of the non-relativistic matter and the radiation. So the radiation is a little bit different because it becomes a relativistic dynamics. But for this spatial time, I intend to show you desirously and assiduously the metric, actually not the metric, but the dynamics of the flat matter-dominated universe and total lifetime of it. So doing such a calculation, here is the integration. And we have to calculate the horizon distance, right? And by using the horizon distance or anything, you can afterwards, you will be able to calculate the total lifetime of the whole universe with the varied types of multitudinous contributions towards the expansion of the universe. So here you can see the other calculations actually. We have horizon distance in here for non-relativistic and matter-dominated universe, the flat universe. And the flatness is because of our assumption, to make it easier. But as this assumption is something consistent with the observation of today's present universe. So the total density of the universe is about 1. That corresponds to the flat case, which is the homogeneity is the key problem for us. And actually, the horizon distance is coming from the scale factor. So the first, you are in that very requisition to calculate the scale factor, the Hubble constant of the matter-dominated flat universe. So how do you do it? Is actually like a Gaussian surface you are working on, like a gravitational distribution, that the whole gravitational material is embedded into the one point in the region. Like this is a globular cluster of galaxies, doesn't matter what it is. The importance is that what consequence is the reason, actually the reason why the gravitational field is there and what causes the gravitational field. So this is a stationary gravitational field, that it is conservative. But we know that there is a kinetic energy. Nothing in the universe is static, but everything is dynamic. So this sphere, or maybe the Gaussian surface, is going to be expanse. So the fields which produced by the gravitational material inside of this field, inside of this region, which they were embedded, are going to be expanded. So it becomes non-stationary case. So you have to calculate it by using the Friedmann equations actually. And those Friedmann equations include the space-time curvatures, the K. You can see from here. There's a K in the formalizations. Those Ks are meaningful and it is prerequisite because it tells about the shape of the space. It has a negative or positive contributions towards the expansion of the universe. For example, if there's an open universe case or maybe closed universe case, then for example, there will be a maximum value of the scale factor, or maybe some critical time where the density of radiation is equal to the matter. Doesn't matter. Or when you put dark energy and its contributions, Higgs fields, doesn't matter. The solutions are going to be changing. So you have to use parametric solutions so as to understand the behavior of it in the whole scene. So what I have calculated is actually from also the MIT and Standford's lectures that are also consistent with, is about 10 billion years from the Big Bang. And the Big Bang is just a model, just an assumption too, but it works by the observational facts and details. And I have found that the Hubble constant is about 97.8 kilometers per second times megaparsecs. And I told you that the time that is required is nearly 10 billion years from the Big Bang. So the horizon distance for flat matter-dominated universe becomes here, 3 times c is the speed of light, and t naught is what we have calculated 10 billion years. So you are just calculating the horizon distance of the universe. And by solving this integration, which is the most general equation that has the contributions of the curvatures, everything, there is no assumption here, little bit. As you can see, this is the most general solution for the total lifetime of the whole universe. And by doing such an integration, we are about to find out that, well, there are interesting solutions and consequences are here, but it's a little bit different. The total lifetime, 2 pi alpha divided by c, and alpha here is here, 4 pi g divided by 3 rho divided by c squared a tilde cube. So I am going to calculate it. I mean, there's some integration here, so I'm using the parametric solutions, and it's going to be solved. So the next one is dark energy, actually, the contributions of that and the solutions of the universe and the behaviors of it as equilibrical solutions.